There's one last detail about inverse matrices that we have yet to really figure out. I keep saying that if a matrix is invertible, it has to be square, and that's really not obvious. It maybe sounds plausible, but I don't think it's obvious. So let's see why that's the case. So let's suppose we have a matrix A that's m by n, and a matrix B that sort of looks like the inverse. Okay, what we're going to show is that, right, just for both of these products to be defined, if the size of A is m by n, that forces the size of B to be n by m. And when I say B sort of looks like an inverse, what I mean is, let's assume that A times B is an identity matrix and B times A is also an identity matrix. Now, one of these numbers, m or n, is bigger than the other, and let's assume that it's m. If actually A has more columns than it has rows, then B will have more rows than it has columns, and so we can just switch the names of everything so that A is the one that has more rows. So without loss of generality, we can assume that m is greater than or equal to n. So what can we say about the sizes of A and B? So our goal here is just to show that they have to be square and the same size. But why is that the case? So we have a matrix A. We have A times B is an identity matrix, right? Happens to be of size m, but that's not super important. Well, in a previous video, we showed that if you have a product of matrices that gives you the identity matrix, that means that the matrix on the left, its reduced row echelon form, does not have a row of zeros. Okay, well, let's suppose that m is strictly bigger than n. Okay, if m is strictly bigger than n, then the reduced row echelon form of A, what could it look like? Well, if it has more rows than columns, how many non-zero rows could you fit into this matrix? Well, the most non-zero rows is if every column has a leading one in it, right? You can't have more leading ones than you have columns, because that's one of the requirements of reduced row echelon form. But if there are more rows than columns, then when you've used up all the columns with leading ones, there are still more rows. And everything below a leading one in reduced row echelon form has to be a zero. So that means there would be a row of zeros. So if m is strictly bigger than n, the reduced row echelon form for A has to have a row of zeros. But according to that argument in the previous video, we know that this can't happen. There cannot be a row of zeros in this reduced row echelon form because A times B is an identity matrix. So that means that m can't be strictly bigger than m, right? Well, if m is greater than or equal to n, but we know that it's not bigger, then that means it has to be equal. So m is actually equal to n, and that means that A is actually a square matrix.